chemical reaction, we know that the voltage of a cell is directly related to redox reaction. Standard reduction potentials and how we use them lead to how we can do this and we can measure this. Just as the overall reaction, so any overall reaction is thought of as the sum of two half-cell reaction, the measured voltage between two electrodes can be treated as a sum of electrical potentials at the electrodes. Now, standard reduction potential is the voltage associated, either with a half reaction or the sum of two electrodes when all solutes are at 1 molar concentration and all gases are at 1 atmosphere, hence the standard part of it. We need to set an arbitrary 0 to compare and have a value of 0 voltage to reference other half reactions. Now, we choose to do that with a standard hydrogen electrode. This is where you have hydrogen in its cation form in hydrochloric acid and in its gaseous form. Now, it could either be a cathode or an anode, but it serves as a reference because we say its standard potential is 0, and everything else can be compared to that. Now, the platinum electrode serves two purposes: one, to be a conducting wire to the electrode, and another one to allow hydrogen gas to react on. So a standard hydrogen electrode can act as both a cathode or an anode. A simple way of putting this is if it is paired with something it's better at being oxidized or a better reducing agent than it, as in the case of zinc, it's going to act as a cathode. It's going to be reduced if it's paired with a better reducing agent. It's going to be oxidized if it's paired with a better oxidizing agent. In this case, it's paired with a better reducing agent because zinc prefers to be oxidized relative to hydrogen. Now you can see the cell diagram is written with the anode on the left, phase boundary, and the cathode. There's only one more dash in the platinum here because this electrode involves 3 states: solid, liquid, and gas. So that's why you have liquid, gas, and solid. Most are just, they look like the left side right here. So how did we know that zinc was the anode in this case? We looked at standard potentials. Now there's a table that you can look at standard potentials for, and we'll talk more about what that table means. But the one with the higher standard reduction potential is going to be the cathode. The convention for finding the total potential of both electrodes paired together is found by taking the standard reduction potential, very clear, the standard reduction potential of the cathode, and subtracting it from the standard reduction potential of the anode. So in this, you can see, because we're using the standard hydrogen electrode as a reference for 0, we can calculate the standard reduction potential of the zinc. Here's another case in which we have a standard hydrogen electrode. In this one, we have the standard hydrogen electrode acting as the anode. Now, why is it acting like the anode? Because it's paired with something that more prefers to be reduced, right? It's a higher standard reduction potential. You can see copper has a higher standard reduction potential. It prefers to be reduced, all right? In this, we can actually get a value for that reduction potential when we pair it with hydrogen, which is a reference of 0, and we can see that it has a value of 0.34. See how this copper cathode has a positive standard reduction potential? And in the previous example, the anode had a negative standard reduction potential. That's not by coincidence. That's to indicate that this zinc serves as something that's going to be oxidized throughout the course of a reaction. And in the case of pairing the standard hydrogen electrode with copper, this is going to serve to be the cathode or be reduced throughout the course of a reaction. Okay, here's the cell diagram for this. Now, there's a couple things to know. As is the case with delta G naught, or delta G with that, that small mark above it right there in the superscript, we can use the sign of delta E naught to predict the extent of a redox reaction. Now, albeit E naught does not tell us if a reaction is spontaneous, E does, not E naught. Okay, so this tells us the extent that a reaction occurs. It gives us a position as to whether the products are favored in the formation at equilibrium or the reactants. More positive it is, the more likely the products of the chemical reaction are going to favor the products. The more negative, more reactants. So E naught gives us a position. Now, there's a couple of things to know when looking at standard reduction potentials. So the E naught values apply for how a reaction is written and it should be read from left to right in the forward direction. Right, the more positive this value is, the greater tendency it is to be reduced. So up at the top, F2 right here is the strongest oxidizing agent. It's the thing that likes to be reduced the most. And way at the bottom, you can see lithium is the weakest oxidizing agent. And it's the least likely to be reduced here. Half-cell reactions are reversible. The sign of E naught just changes in magnitude. So if I have iron right here and it's undergoing reduction, the sign is 0.77, positive 0.77 volts. If iron happens to be undergoing oxidation and this reaction is flipped, the standard potential just changes sign and it becomes negative 0.77. Now, one thing to worry about with the sign of delta E changing, that equation that we had previously that said E naught of a cell is E naught of the cathode minus E naught of the anode. This is all with reference to standard reduction potentials. So you can do one of two things. You can just use standard reduction potentials and use this formula to get the potential for the overall reaction, or you can add up the standard reduction potential with the standard oxidation potential, but you'd have to remember to flip the sign. You'd scrap this formula, you would just add them together, but you need to make sure that you flip the sign. This formula makes it so you don't have to worry about any of that, and you can just take the reduction potentials. You keep it in reduction potentials, and you subtract you subtract the anode from the cathode. Now, changing the coefficients in a reaction, say you're balancing a redox reaction, you have to change coefficients. It does not change the value of E naught. So these values do not change with changing coefficients. They get flipped when you reverse a reaction, but they do not change with changing coefficients. So let's use our new knowledge to predict what will happen if bromine is thrown in solution with chloride ion and chloride ion and iodide ion. Both of these will be anions in solution. That's important to point out. As you can see, this table shows all the standard reduction potential. You have bromine in solution, and you have the chloride ion and the iodide ion. Right? You don't have I2, Br2, and Cl2 all in solution. No, you have bromine with these two. Now, being that this needs to occur in the forward direction, this must serve as the cathode. This is asking you, all right, let's use the diagonal rule. Now, what is the diagonal rule? The diagonal rule tells you that anything that is on the left side of a standard reduction potential will spontaneously react with something lower than it in this chart to the right side of the arrow. So let's say silver and iron, just to be really close and concrete. This silver species right here will spontaneously react with iron 2+. The silver serving as the cathode because it has a higher standard reduction potential, and the Fe2+ serving as an anode. So we use that diagonal rule to look at bromine. You'll see that it will spontaneously react as the cathode, and it will make the iodide anion the anode. It will not spontaneously react with the chloride anion because it's above it in this table. It does not follow this diagonal rule. So this is the observed reaction. Right? It will not oxidize Cl-. Right? It has a higher standard reduction potential. So the chloride has a higher standard reduction potential. It's going to want to be the cathode. Br2 needs to be the cathode here. So it can only be the cathode with something that has a higher standard reduction potential then. And that would be the iodide ion. Let's work with another example. Galvanic cell consists of a magnesium electrode in a 1 molar magnesium nitrate solution and a silver electrode in a 1 molar silver nitrate solution. Let's calculate the standard electromotive force or voltage of the cell at 25 degrees. So we look at, sorry about the arrows being a little displaced. We look at both of the half reactions and we can see that one clearly, the silver clearly is a stronger, oxidizing agent. It more likely wants to be reduced than magnesium. So the silver would be the cathode, and I would peg magnesium as being the anode. Okay. Magnesium would be the anode. Silver would be the cathode. I'd add them together. And I would take the standard reduction potentials of the cathode minus the standard reduction potential of the anode. Okay. See how that minus sign makes this positive? You can see that this positive value of E0 shows that the forward reaction is favored. There are more products than reactants at equilibrium.